Okay, let's do problem 133 clone graph. In this question, we are given a reference of a node in a connected undirected graph, and we need to return a deep copy of the graph. So let's see what we are given in this question. So we are given definition for a node. So class node contains the value of the node and list node of neighbors, and each node's value is same as node's index, and it's one indexed. And then we are given neighbors like this. So if we write down one index notation, we have 1, 2, 3, 4, and that means this node has value of 1 and neighbors of 2 and 4. This node has value of 2 and neighbors of 1 and 3. If we use this, we can generate our graph as we can see in the question. So there are a couple of things we can't do and we have to do. We can't return the same graph, and we have to return the graph with the same connections. So this is the original graph and this is cloned graph. So this should be 2 and this should be 3. So these are jumbled up, so we can't return this. And we also can't have reference to the original graph. So suppose somewhere in our function we are looking at this node called node. And if we do node new node equals node, what we are essentially doing is we are essentially creating a reference to our original graph. So we can't do that. Instead, we have to use new notation, and so that our new node is a deep copy of the node. So that if the original graph is gone, this new node is still valid. So let's come up with a solution. So suppose we write our function and then we took the first node as an input. So we can clone a new node using the notation we just saw, and then we have to add neighbors. There's an issue with adding neighbors. So if you do new node neighbors equals node neighbors, because we haven't cloned the neighbors yet, what we are essentially doing is we are creating a reference just like we did here. So this part is wrong. So the issue is neighbors aren't even cloned when we're looking at the first node. So the question is, what should we do? The answer is we have to create hash map and use recursion. And let's see how it helps. So I came up with a very simple solution. We have node 1 and 2, and node 1 has neighbor of 2, and then node 2 has neighbor of 1. So in our function, we clone a new node and then add to hash map. So hash map is of type node and node. So it contains original node and it contains clone node. And then we came up with this logic. If neighbor exists in hash map, we add the clone neighbor, but node 2 isn't in hash map, so it goes to else statement and then add function recursion. So we recursively call this function. And then since the function returns a new node, the recursed function will return cloned node 2. So it makes much sense if you look at the recursion like this. So we create a new node and add to hash map. So we have 2 here, and we add it to hash map. And if neighbor exists, yes, neighbor exists, so we add this clone node 1 as a neighbor. And then we return new node so that we can add cloned node 2 like this, and then we return new node as an answer. So let's verify if this approach is correct. So we are starting at node 1. So we clone node 1, add to hash map, and then because it has 2 neighbors, we're looking at neighbor 2 and 4 in order, but neighbor 2 doesn't exist, so we recursively call this function on neighbor 2. So again, doing the same thing, and then the thing is neighbor 1 exists in hash map, so we can add it as a neighbor, but neighbor 3 didn't exist, so we can recursively call neighbor 3. Again, from 3, neighbor 2 exists, but 4 didn't, so 2 is added as a neighbor, and then we're recursively calling on neighbor 4. And then when we're looking at node 4, both 1 and 3 exist, so we can add as neighbors, and then we simply return back. So when we return, when we are returning, so we're returning clone neighbor, clone node 4. So we are adding clone node 4 here, and then we are also returning clone node 3 to here. So we are adding clone node 3, and then again returning clone node 2, so we can add clone node 2. And the neighbor for loop that was pending, so now we can see that neighbor for exists in hash map, so we can simply add clone node 4, and then we can return clone node 1 as an answer. So what's our final pseudocode? We clone new node, add to hash map, and then use for loop for both neighbors. And if neighbor exists in hash map, add clone neighbor, else recursively call the function. So we can now do some coding. So we have clone here. So we need to create a function, private clone. And in our main function, we can handle one edge case, say that if node is null, we return node. And we can create hash map as well. It's going to be called map. And then we're going to recursively call this clone method. And then we're going to return clone node. So clone node is the output of clone method. So it takes in node and map. So this notation should be like this. And then we're going to follow the steps we have here. So clone, add, for loop, if, else. So it will look like this. So we create a clone, create a node, add to hash map, iterate through neighbors, check if neighbor exists in hash map, and then if so, we can just add the neighbors, else we recursively call the function. Okay, so let's run the test. Okay, let's submit. All right, I don't know why it's giving me 50%. It constantly changes. Yeah, it's went up to 84, but if the internet is good, it's gonna be 99 something. When I ran it was 99. But let's quickly revise why we need hash map. So if we encounter the same node again, we don't need to recurse. We can simply add as neighbors, as we can see here. And it creates one-to-one mapping, so it keeps track of exactly one clone for each node. So the time complexity is we are cloning each node, which is vertex once, so it's O of V, and then each node iterates over two neighbors, as we can see here. So it's O of 2E, E for edges. So we ignore this 2 here, so the time complexity is O of V plus E. Okay, so that's it.